Right. So we'll see that, I'm going to select this particular inverted T, and we see how this can be included with the springs. And if you look at the spring constant, you see that the modulus of subgrade reaction is with a factor of safety of 2 multiplied by 40 multiplied by 120 will give you 9,600 kilonewtons per meter cubed. And if you are going to apply one spring over 0.5 meter length, we divide it into 0.5 meter length. The reason is we are having lengths like 4.5 meters, 5.5 meters. So it's convenient if we divide it into 0.5 meter lengths. And then we can say that each spring will represent 9,600 into 0.5 into 1.8. 1.8 is the width, 0.5 is the length. So the area represented by each spring is 0.5 by 1.8. So the spring constant will be 9,600 multiplied by 0.9, that is 8,640 kilonewtons per meter. What this means is we need a load of 8,640 kilonewtons acting vertically to generate a settlement of 1 meter in the soil underlying this particular building. So we'll now look at the model, and first I will unlock the model. And save this file as BU3 so that we'll have and then I'll save it as BU4 as well. So we have something identical, and then I will draw this foundation, and before drawing the foundation I will convert or get rid of all these supports. So I will assign no support to all these. So there is no support now. So now what I have to do is select one of the planes, and also what you have to see is that on the outer frames, if you want, you can use a smaller T section. So save this and open BU3, analyze it. And if I view the outer frame at y is equal to 0 and ask it to show the forces, service combination 4, axial force. On the outer frame, you can see the axial loads are much less. That is 498 plus 261. So that is 498 plus 261 into 2 divided by 107.5 divided by 14.9 will give only a value of 0.94. So we can have something like 1 meter wide T for the outer frames and 1.8 meter wide beam for the T beam for the inner frames. So we look. Open the next file, BU4. This is the one that I'm going to apply all these frames. So we have defined two sections, frame sections, and I can add a new property. I can go with the beam having a width of 0.45 and a depth of 1 meter, and B2 is 1.8, and this is inverted T 1800 1000, and we can see D2 as 0.7 and D6 as 0.3 and all the other values as 0. And then this B2 as 1.8, B3 as 0.45. Okay, now we are getting the T, and I'm going to say it's a foundation concrete. The reason is foundation concrete has no weight because we have already used the net bearing capacity. So it's foundation concrete. And I can also add a copy of that, and that is inverted T and 1000 by 900. For the outer frame, I'll use a lesser depth. So this is 0.9, and the width is 1, and this is 0.6. So you can see it's the inverted T. See, okay, and display undeformed shape. So here I can draw it. This is the ground level. So I'll draw this, and when I'm drawing, it's useful to have 3D view active so that I can see what's going on. So I can draw it here as well. I'll do that. So what I do is I will select those three and divide frames. Divide into 4.5 means 9:1, and this is 5.5, so I have to divide it into 11:1. So I can just check the coordinates. So that is 0.51. Here you can see the coordinates appearing 0.51, 1.5, 2, and here you get 4.5, 5, 5.56. It goes on like that. So I can select all these and assign the frame section, inverted T, this one, and here I can ask it to extrude it so that I will be able to see the shape, and you can see the shape of it. And then I can replicate this at 4-meter interval 2 times or 3 times, and I will also replicate it -4 once, and then I will select these two and allocate, assign the other section, and that is the smaller one. So now you get the inverted T sorted out, and you can see I have not connected it this way. So for the time being, we will not connect. So it's only the inverted T going in one direction, and then you can ask it to this is located x is equal to 0.5. This is 4, 8, 12. This is x is equal to, see, the column is now it looks right. It was just a graphical problem. So you can see it's all okay. So now the model is okay, except that I have not allocated the spring constants. So the spring constants for all these will be 8,640. Assign, joint, springs, global, 8,640. And for the 1 meter wide one, that is 9,600 into 1 into 0.5. So these ones, the spring constant is 4,800. Assign spring constant of 4,800, and that comes with 120 into 4 into 40 is the spring subgrade modulus, which is 9,600. 9,600 multiplied by 1 meter by 0.5 is 0.5 meter is 4,800. So you get the spring constants. So all these, the full model is now with the springs, but I have to do something now, and that is to make sure this structure does not move. So which means I will have to allocate, make sure that these locations has some restraint, And the restraint is, I would say it cannot move in X and Y directions. And I will also have to say these locations, it can move only in X direction. It cannot move in Y direction. It can move in Z direction. So I would say that it can move in X. It can move in X direction. It cannot move in Y direction, and it can move in Z direction. So the structure can move this way, but it cannot move this way. So all the movements will be in this direction. So now the structure is ready. And if I say just don't extrude, and here you can see the model with all the springs. So now you have the model with springs, and I can actually analyze it now. And you can see it shows a big deformation vertically, and it has deformed 5.5 millimeters vertically. And whereas here it has moved by 5 millimeters vertically. So when you look at the graphics, you see a big deformation, but it can be only a very small one because it's a relative deformation. And here you can see the structure has moved downwards vertically by 5 millimeter, 5.3 millimeter. So now if you look at one of the frames, one of the internal frames, and you will be able to see the bending moment diagram due to the service conditions, if you want first. And you can just have a look at the axial forces as well. Sometimes they would have changed slightly. And you can see the axial forces have changed slightly. Because of the deformation of the structure, the axial loads have changed slightly. And accordingly, there will be some minor change in the bending moments here as well. And then I can also look at the bending moments. And due to service loads. And I can also look at the reactions, joints, service combination, and look at the reactions. And if I look at the reaction values, here you can see the reaction is about 110 at the corner, which may not be worrying, but let's see this one, 107. So if the reaction is 107, 107 divided by 1.8 divided by 0.9, sorry, 0.5, 107 divided by 1.8 divided by 0.5 gives a soil pressure of 118, gives a soil pressure of 118. And if you look at here, it is 105. And if you look at here, it gives 97 divided by 1.8 divided by 0.5. So here you get 107. So basically you can see the width of the foundation selected may not be adequate here because the soil pressure, the net bearing capacity is 107. And because we ignore the weight of the foundation, the soil pressure in these areas also should be below 120. But when you allow for the the weight of the foundation, we found that the net bearing capacity is 107, whereas here you get something like 107 divided by 1.8 divided by 0.5, so you get 118, which means the bearing capacity has been exceeded in these areas. But in this analysis, sometimes we don't worry too much about the edges, because in the actual soil behavior, not only the soil here, the soil beyond the foundation also act along with this foundation. So because of that, if you have a minor variation here, it is not going to cause a major problem, because the soil in this area also will be participating in resisting this load. So you will find that the stressors can disperse in this direction, and because of that reason, sometimes if you get a minor violation here, it may not be a major problem. But if you want, you can actually increase the width of the foundation to 1.9 meters, but for the time being, we'll stick with 1.8 value. And here you get, here in this area, you don't get a problem. And so as in the middle of it, you don't have a problem. So the bearing capacity is not exceeded in these areas, but there's a minor violation at the edges, which may not be a major problem, considering the fact that the soil in this area also can participate in resisting the load transferred at the edges. So up to this point, do you want to ask any question? Up to this point, do you want to ask any question? Dean, do you have any question? Or Nuan? Shamil?
No, sir.
No? Okay.
Only is one issue that not regarding this foundation, but can't we just apply the loading on slabs?
Yes, if you want, you can add loading on the slab, but you have to make sure the slab is meshed. So basically, you have to see that if I take one of the floors, if you take this floor, if you look at this particular slab, you can see that element is connected only at these 4 nodes. So if you are going to apply the load on the slab, then you have to mesh the slab to say 0.5 meter or something similar. And then you have to also make sure these beams are divided at those locations so that the slab is connected to the beam. But when you consider the slab is connected to the beam, the stiffness of the beam will increase. So to compensate for that, you have to go there, go to the section properties of the area section, and you have this one. Okay. So you have to go there, go to the define area sections, and so here you can see something called set modifiers, and you have to go to the set modifier and make sure the bending to modifier is 0.25, and this 1 modifier is 0.25. So basically you have to make sure that the stiffness of the slab is reduced by 75%, so that it will not unnecessarily stiffen the beam. So you have to make those modifications, and also what happens is when you do that, you might get reasonably close answers, but the model will become very heavy. Because all these shell, now here you have only one shell, but if you divide it into 0.5 meter interval, and then you get large number of shells. So that's why I have not done it. But in more dedicated programs like ETABS or Midas Gen, the program has facilities to do the meshing while it is running. So basically, because of that reason, and in Midas, it actually allocates the loads as we have done automatically. Whereas in ETABS, it has the facility to do the meshing while it's running the program. So those programs, you can just apply the slab and say while running, divide it. So it will divide it and then transfer the loads. But in this is sap2000 is a general purpose one. So because of that reason, I have gone with unit loads. But if you want, you can divide the slabs into 0.5 meter by 0.5 meter segments, and then divide all the beams also to the same segments. The moment you do that, you can have the connectivity between the beams and the slabs, and then you can actually apply the loads on the slab. Only thing is the model will become rather heavy. So have I answered your question?
Yes, okay, thank you.
Right. So we'll analyze this again. So basically, if we want to design this as an inverted T, so what we need will be the moment not under service conditions but under ultimate conditions, because we will be designing the inverted T for those. And display, we need the load under ultimate conditions. So you get the bending moment diagram, but again, we look at the frame at y is equal to 8. That is one of the middle frames. And here you can see the bending moment diagram. And if you enlarge it, you'll see that, get the values like 118. And let's see what's the value that I have included in the note. So this also looks similar. And you can also see this spring constant of 1640 assigned under each joint. And the bending moment is considered as 409 here, 427 here, and 432. And if I look at this, and I have considered it as something like 410, and here I have considered it as 427, so get 405. But on this side, you will get 423. So I have considered 427 because I have used another version of the model. So I got 427 there. So here you get 449. So what I do is, shall I reverse back to that particular model, because then it's easier. The reason could be that, you know, I have actually allocated a different width here, and because of that there might be a small change in the forces. And if I look at the first I'm in the lecture, I'll give a call after the lecture. Okay. So if you look at view, the outer one, and display, and here you can see the moments are smaller. Where the loads are smaller, the moments are also smaller. So what I do is I'll save. I'll open the model that I have used earlier, that is 6C. And if I ask it to, it's already analyzed. And if I view this particular frame, and analyze it, or no need to analyze, it's already analyzed. And if I ask it to display, and here you can see the values of 1 and 9. And if I look at this particular one, here you can see 427, and here you can see 432. So those are the values that are used in the note: 409, 432, 427, and the spring constants, the spring values have been displayed, joints, service comfort. You can see here the values are lower, so they are within the limits, something like 96 divided by 0.5 divided by 1.8 gives something like 106. So these values are okay, 107. And then here also the stresses are lower. Then I can ask it to display joints, comfort as well. I'll get higher values. But now when you want to do the design, you can actually use the values in the envelope. But just to keep things little simple, I have actually used this combination for the design. But if you want, you know, you can actually use the values due to envelope in x direction, envelope in x direction. Can use the moments due to the envelope, and you can see if you look at the values, you see they are not drastically different. They're pretty close. So you can see the maximum moment is about 435, whereas I have used a value of 410 to do 409 to do the calculation. So you can use these values in the actual calculation. But just to keep things simple, I have used one combination which is reasonably close to the maximum values to do the calculations. So that's something that you can observe. So I'll go back to the combination 4. You can actually use this particular one. And when you use this envelope X, you are taking into account the wind load effects as well. So those are the moments. And then you can also look at the shear forces. And that is shear 2-2. And you can see it, you get it in steps. The reason is the structure is discontinuous at all these locations. So you get the shear force acting not as a distributed load, but as a point load. So because of that reason, you get this. But you can always consider that it's going to vary linearly from one end to the other. So when you are doing the shear calculations, you can consider that's going to vary linearly. So those are things you can see from the model. So if we look at the note now, so here you can see the bending moments are in that range. And if you look at the shear force values, you see the shear force values are like 569 and it varies 449 and this region 328 and so on. So you can see the shear force diagram, and on this side you get 577, 578 and so on. So you have a shear force diagram and a bending moment diagram, and if you want you can go with the bending moment envelope and the shear force envelope as well. And here you can check the reaction from the ground, and when you check the reaction from the ground, you can also see whether you are violating the bearing capacity or not. If you are violating the bearing capacity, that's an indication that it's better to increase the width of the base. And when you are increasing the width of the base, you can do it only for the two end spans, and you can keep the width in the middle span as it is, because the violations occurred only at these two ends. So it can be the load can be carried by the foundation of this is with the net bearing pressure is 107.5. With the bearing pressure of 107.5 is 96.75. So it is more than this value. So there's no failure in the foundation. So if you look at the ultimate loads on the springs, in this area, it's about 144 kilonewtons per meter squared, whereas in this area, it is about 130 kilonewtons per meter squared. And these values will be useful when you are dealing with the shear calculations. So this is the modeling part and the foundation on springs. And for the edge, you can use one width. For the middle ones, you can use a different width. So when you change the width, you can see the middle ones might need a width of about 1.9 meters or 2 meters, whereas the outer ones can be of 1 meter width. 1 meter width. So once you have all this information, you can find the reinforcement, check for shear, and all the calculations can be performed. And then you can also check this as we have done earlier. you can do all the checks we have done. So I'll very briefly go through the checks just to refresh, because last time we had to rush a little bit. So now you know the bending moments are in this range and the shear forces are in this range. And so you can find the reinforcement. It's not anything special. And also for the two spans, you can find the two different effective width for flanges that we discussed last time in detail. So I'll not. And also in every span, you have to check the minimum reinforcement. And here you can see I'm using 0.13% because we are using 25 megapascal concrete. And these are the flange widths. And then the reinforcement. Again, the minimum reinforcement check. And then the transverse reinforcement. So in the transverse direction, if you look at this particular section that we selected, it has a width of 1.8 meter here. This is 0.45 meters. So this outstand is 0.9 meters multiplied by 0.45 divided by 2. That is 0.675 meters. So here 0.675 meters. And the pressure that we expect from below is about 144 kilonewtons per meter squared. We can get a pressure of about 144 kilonewtons per meter squared. So based on that, we can work out the flexural moment. So the outstand is 0.675 meters. The bearing pressure is 144 kilonewtons per meter squared. So based on that, you can work out the bending moment. And bending moment is bearing pressure multiplied by 0.675 multiplied by 1 multiplied by 0.675 divided by 2, 32.8. And with a 300 millimeter thickness with 40 millimeter cover, you get an effective depth of 252, which means there's no problem with the outstand. That is the flange section, there's no problem. And you can see what you need is only about 12 millimeter bars, because we need only a very little reinforcement in the flange, and that's the usual experience when you get the low bearing capacities. But if you are getting high bearing capacities, then the width and heavy loads, high bearing capacities, good soils, then you'll find the reinforcement in the flange can be fairly high, like something like T16 at 200 or T16 at 250. And whereas in this particular case, the soil pressure is low, and because of that reason, you can see the reinforcement requirement is also fairly low. Then we can also see the vertical shear force at the internal column to prevent crushing, and that is based on this column load of 577. And so based on that, you can work out the punchy shear effect, the direct maximum shear effect, direct shear effect. So with angle of 22 degrees, you can work out the maximum shear force that this can resist, and that is 1155 kilonewtons. Whereas at the face of the column, you get a force of only 530 kilonewtons. And in the internal column area, we calculated that the pressure is 130, soil pressure is only 130 kilonewtons per meter squared. So you have to multiply it by the width and multiply it by 0.2 meters, because the column is 400 millimeter by 400 millimeter. So at the face of the column, the shear force is only 530 kilonewtons. So you can check at the face of the column, what is the shear force carrying capacity, and the shear force carrying capacity depends on the cross section of the web of the beam. Web has a width of 450 millimeters and it has effective depth of 920 millimeters. So the shear force carrying capacity, maximum shear force carrying capacity is 1155 kilonewtons, whereas the actual shear force, maximum shear force is 530. So there is no problem, and you can use 22-degree angle for rest of the calculations. And then you have to see what is the most critical location, and you can see in the center span the shear forces are higher, so you can check shear in this one, and we have to select shear at a simple D away from the face of the column, and simple D is 920 millimeters plus 0.2, so you have to select 0.2 plus 0.92, 1.12 meters away. You have to select the shear force, and that is 577 minus. I have assumed that the soil pressure in this area will be around 130. So I have deducted 130. Width of the base is 1.8. The length to this particular critical section is 1.12. So once you deduct the upward force from the shear force, you can find the shear at this particular location, which is about 340. And for this, you can decide the ASWS ratio based considering that we are going to provide reinforcement in the base, and ASWS ratio for this particular shear force of 314 is 0.35, but you have to also check the minimum links, and when you check the minimum links, what you have to provide minimum for ASWS is 0.36. So if we select 10 millimeter links at 300 centers, you can get ASWS of 0.523, which is more than both these values. And when you are providing that one, you can calculate what is the shear force carrying capacity, and you can see the shear force carrying capacity of this particular reinforcement of 10 millimeter bars at 300 centers is 469. And if you look at the shear force diagram, when you have 469, the critical section might have something like 377. The 469 is more than the capacity that you need in this span as well as this span. So which means you can just select a minimum reinforcement of H10 at 300, which is a reasonable spacing, and you can provide that particular reinforcement throughout the length of the foundation, but you can also provide less, but it does not look right because you have compression reinforcement as well, and when you have compression reinforcement, the compression reinforcement will need anchoring. The maximum distance is 12 times diameters. So generally it's a good practice to make sure something like 12 times diameters, you'll get some constraint for the compression reinforcement. So actually it can be even reduced to something like H10 bars at 250 centers, because we have used H20 bars, and some of these bars can be in compression. Oh, we have only the tension. I think we have only the tension, so it's not a major problem. Even this H10 at 300 is okay because we don't have any compression reinforcement in the beam. So because of that reason, H10 at 300 is also okay. So you can see that shear is not a problem at all. When you provide H10 at 300, the shear carrying capacity is 469, and you can see when you look at the shear force diagram, 469 is a reasonable value. And also you have to check this additional longitudinal force, additional longitudinal force due to the shear. And here again, I have considered that the shear force is 314, and based on that you can work out the additional reinforcement needed to carry the shear. So whatever the reinforcement that you provide here at the top, you will not curtail it, and you will just allow it to go through the support as well, so that automatically the extra reinforcement requirement for carrying shear would be satisfied. So that's okay. But in addition to all this, when you look at this particular section, when you look at this cross section that we selected, there can be another type of failure, and that is, now we provide the transverse reinforcement this way, we provide the transverse reinforcement this way, but in addition to that, at a distance d away from the face of the web, we have to check the direct shear under this, in this section. So direct shear occurs here due to the loads acting in this area. So the outstand is 675 millimeters and the effective depth is 252 millimeters. So over a width of 423 millimeters, you get a load of 140 kilonewtons over a width of 423 millimeters. So you get a shear force of 59 acting here. And if you divide that 59 by 252 by 1000, because the shear force is over 1 meter length, you'll find the shear force here is only 0.23. And we know always concrete will have a shear carrying capacity in the range of 0.35 and above. So which means the direct shear failure cannot happen here. But if you look at, I have modified the note last week. And if you look at what we discussed last week, you would have found that the direct shear cannot be taken in that particular problem because the soil pressure is very high. Whereas in this problem, you can see the soil pressure is low, and because of that reason, the shear is not a major problem in the flange. So with the flange, vertical shear in transverse direction, here you can see the shear force is 0.675 minus 252, 64.8. That is 0.675 minus 0.252 into 144. That is 60.9. 60.9. I have got it as 64.8, which is slightly higher. And then divided by 1000, divided by 252, you get 0.24. I have got 0.257. So basically it's in that range. And the important thing you have to notice is it's not going to fail. It's not going to fail because the shear carrying capacity is about 0.45 in this particular area. So thickness of the flange is adequate because we have selected the thickness of 300 millimeters. So in addition to that, you have to think about this vertical, the shear failure between the web and the flange. And if you look at it, you can see that also cannot happen. We discussed how to calculate that in detail, so I will not spend time discussing that. So with that, you can see that inverted T-type foundations can be designed with modeling the whole structure and then representing this, representing the foundation as a set of springs, spring supported inverted T-beam. And then, if you want, you can extend it in the other directions as well. And if you want, you can convert it to a raft foundation as well. So we'll discuss those variations next time. And so if you have any question, you can ask. And if you have no questions, then I will end it.